and I hope I'm audible. All right.
Yes.
So, well, this talk is it's a very difficult task to make a presentation for this task because it's not this talk because it's not about one particular problem that we solved or one particular solution. It's about uh, it's about a set of learnings that I received while doing my PhD. To summarize it in one sentence, so it's about various things, but I would try to what I have tried to do is from the paper, I have tried to pick up few learnings that I had and then try to summarize in this talk. So I hope I'm able to do justice to the same. So pointer analysis, well, Michael Hind in 2001, this was a famous question. Haven't we solved this problem yet? This was 20 years, more than 20 years ago, where he pointed out that no, even though we have been doing it for 30 to 40 years, we probably have much more still to be done. And interestingly, this happens to be true even now. We see papers in almost all the conferences in our area, ECOOP, UPSLA, CC, this splash, multiple conferences in this splash as well, where we see some or the other thing being done in pointer analysis still. And why that's the case, it's interesting because the problem is that precise pointer analysis do not scale over large programs, and this problem holds to be true even now. In general, pointer analysis that are precise in multiple dimensions, they do not scale over, well, real world applications. That has been a big problem. So my journey with pointer analysis started with my first research meeting in 2014, where we discussed, okay, there are things in JIT compilers where you can't scale stuff, or you can't perform precise analysis, and the problem is even more exaggerated than in static compilers where your time budget is more. So that's where we discussed this problem and started doing something. In July, I submitted my first paper to POPL. It got rejected. May 17 rejected, June rejected, October rejected, never stopped. April rejected, 2018 rejected. Well, this was multiple works, but after facing so many rejections, well, the magic started happening in 2019, where we had a paper in CC, then in ECOOP, then in UPSLA, Dopla's paper was presented, then CC. So something, what started happening again? So what happened over these 5 6 years that led to more work getting accepted finally, and not only being accepted but also being applied in real world compilers. Some of my work is being applied in OpenJ9, Eclipse OpenJ9 now, and my prototypes were also in Hotspot C2 and so on. So what were the challenges that were not known as a PhD student, and what were the things that are leading to even more work happening along with my students now in the last few years post the onward essay. This was the topic of this onward essay 2 years ago that I'm going to discuss today. Okay, so what did I learn by doing all this? So, well, the essay is basically organized into three major topics or three major categories. First is when we start as a new PhD student in this exciting area, what are the misconceptions in our mind when we move from a classroom setting to a research implementation? Then second is, okay, we have some cool idea. Let's say we implement the pointer analysis, but then it doesn't scale. We find when we run it over benchmarks, the implementation is over. When we run it over benchmarks, no, it's not scaling. It's not terminating. It's just taking an infinite time. So some of the things which I have been part of to impart efficiency to pointer analysis, and then how do we argue correctness about some of the things that we do. So these are the three categories under which this paper is organized, and I'll try to pick something or the other from each of these, and you're encouraged to learn about many more in the paper. So, well, first is about clearing some misconceptions, as I promised. So, well, by assignments, I mean course programming assignments. So, as a PhD student, we take courses on compiler design, program analysis, maybe just-in-time compilers, and so on. And then when we start doing something in, say, Suite or LLVM, something which requires you to handle a complete programming language instead of a subset language that was designed specifically by the instructor for you to learn the concepts, there is a lot of challenge when we apply it in the real language scenario. For example, we are usually taught, not only at my university, I have seen this at many universities, in fact myself as an instructor now, we tell students that there are four kinds of statements that you need to basically handle: standard Anderson's analysis, new or malloc, copy, store, and load, to when you want to write a pointer analysis, right? But I realized while taking it to Java, let's say, that no, there are many more that you have to handle. what happens when you assign null? Is your analysis flow sensitive? Is your analysis flow insensitive? If it is flow sensitive, then probably you need to model null as a special object which may represent a possibly null value being pointed to by a reference variable. What do you do with exceptions? Do you even model them in your control flow graphs, or do you don't? I know many research papers, in fact, where the works have come out, they are nice, but they do not handle exception edges. And hence, when you want to apply this to a real world JIT compiler, if you did not handle the possibility of exceptions or exception edges being present in your control flow graph, probably you have missed something over there. Well, intra-procedural is not the only one. You have inter-procedural analysis. Even this ate up my mind for at least 1 week. Well, there is a this pointer, hidden this pointer here, which usually IRs do not make explicit as well. So you have to handle them further. And then of course you have a return statement which you need to handle. So there are multiple things apart from just new copy, store, and load statements. And I was performing escape analysis, so I had to handle synchronized constructs, global variables. Globals are very interesting. Whether to model the heap reachable through globals or not, it's an interesting question. So I had at least 14 cases to consider in my first research prototype pointer analysis, and the first. This is the first learning I had while beginning to write analysis, that okay, it's not just 4 statements, it's much more. It even though we learn a very simple pointer analysis in a classroom, you have to handle much more when you go to a big programming language. Well, fine, it's very simple. As we go ahead in the talk, I'll talk about some deeper insights as well. So more starter tips are in the paper. Uh, First is, okay, most of the pointer analysis we implement as graphs. We are taught, first question when you are taught about a graph is, you should ask what does the node represent in the graph and what does an edge represent in the graph. Well, most of the times we implement pointer analysis, we don't have nodes. Sometimes we don't even have edges. We implement them as in the form of bit vectors and so on. And again, these are a few things which are not taught to us in programming courses. Right? Then second is, we are taught this nice work list based fixed point data flow analysis, and we try to apply it everywhere. But when I read many research papers, well, IDFAs do not scale. That's the main that or IDFAs are a major hindrance behind scaling. Well, but we need IDFAs, but do we always need IDFAs? Sometimes IDFAs are not needed. There are several analyses, like the pre-analysis applied in Yanis is sitting here in their group's papers, one of my other papers. You don't need flow sensitivity. You don't need an IDFA. That was one other thing which I learned in the beginning, that okay, you probably don't need all that power which you are taught it. You are probably making it more complicated than it's needed. Right. All right. So beginner tips over. You implement a pointer analysis. How do you impart efficiency to various sensitive pointer analysis? For example, field sensitivity in Java is almost a de facto. Without fields, we can't compute any useful information. Flow sensitivity affects precision positively, but scalability often negatively. Intra-procedural analysis are often not enough. As I said, JIT compilers typically go with intra-procedural analysis and end up doing very few optimizations that could be done by inter-procedural analysis. And once you go to inter-procedural analysis, probably the most interesting thing that comes in your mind is context sensitivity, which has been shown to be very useful, especially for object-oriented languages, but it throws scalability off the cliff as soon as we are context sensitive. Right? So let me give you an example of the most interesting, as if we agree is context sensitivity over here. Let me give you an example over here, and I would try to tell how did we impart efficiency to context sensitive pointer analysis. Let's say I have a class A here with two fields f1 and f2, a method foo, which calls the method bar at two places here, and bar in turn calls fb, which let's say doesn't do anything interesting about pointers. All right. So if I am using standard call strings based context sensitivity to analyze this program, I would create two contexts for bar at line numbers 5 and 6 respectively. And for each context of bar, I would create two contexts for FB. When I start analyzing bar at line 5, I would create two contexts for FB at lines 11 and 12, and the same when I start analyzing bar. So there are two contexts for bar, four contexts for FB over here. And I'm sure all of us are aware of the problem with recursion when we try to just increase the length of the call strings infinitely. When there are recursive calls, the call string doesn't terminate, and you don't know where to stop, how much how long should you go and analyze context using the using the call strings approach, and hence we put usually a limit. We say we would terminate after k, and after that we would merge all the information coming from higher values of k, right? So this is the standard way to perform KCS, and usually it's known that beyond 2 or 3 it doesn't scale with a precise modeling of the heap. Context sensitive analysis with higher values of k for the call strings abstraction do not scale. So there is a very interesting, not very well known, but very interesting notion of value context, which was proposed long back in CC 2008, as well as a few other papers for their related ones. So what do value context do? They say that, okay, keep modeling call strings, but then since call strings can grow infinitely, what if the data flow value entering inside a function is same as some other context that you had analyzed with a different call string? They say you terminate. You do not reanalyze the method if the data flow value going inside a function is the same as some previous context, and they call it the context abstraction is called value context. So what happens here? Let us assume a trivial, well, not a, let us assume a hypothetical points to graph at line 5. Before analyzing bar, the variables a, b, c, d are pointing to some objects, and those objects fields are pointing to other objects, and dot dot dot. Right? The value context approach says when you start analyzing a function or a method, in this case bar, you look at the value, the data flow value reachable from the parameters, and you use that as the context. Now, here p corresponds to the variable a, so whatever is pointed to by a is pointed to by p over here, and the receiver, the this pointer corresponds to c, so whatever was pointed to by c in the points to graph at line 5 is pointed to by this when I start analyzing bar, and I would store this as the value context in under which I would analyze the method bar. At line 6, after the update p dot f1 dot f2 equal to x, there are edges added from the objects pointed to by a in the source program to, let's say, another object, new object, which I'm representing using the line number at which it is allocated, 09. So this is the modification that happened in the call made to bar later. And the value context corresponding to this call would again be whatever is pointed to by p and this in the call made to bar at line number 6. So this is the value context. Now, what does the value context approach do? Well, the value context approach would compare at each call site the current context, the current value context with all the existing value contexts. If it is matching one of them, it doesn't create a new context for the method, else it would go and create multiple contexts. So value contexts were not used for points to analysis earlier. They were used for various constant information. I mean, I would say non-heap analysis, which have simple values, simple data flow values at call sites, right? So we like the idea, well, because here you have no issues related to recursion. The analysis is guaranteed to terminate if the set of data flow values form a finite lattice. But we found that when we tried to apply this to pointer analysis, we had some application for which we needed a very precise context sensitive pointer analysis. When we tried to apply it there, we found that even on a 512 gigs of machine with a good enough number of CPUs, the analysis do not terminate even over the simplest da capo benchmark. The analysis don't terminate in several hours. We found, okay, it's a nice approach, but it doesn't work. What to do now? So they are precise enough, but do not scale for pointer analysis. So then we came up with an approach where the steps are more important. It's not about this paper, but the steps are more important, which I would conclude as some general observations at the end. So first we tried to identify relevance. Well, we have large points to graphs at various places. Is the whole points to graph that's reaching bar at its call site relevant inside bar? What do I mean by relevant over here? So let us say this was the value context which reached bar. Now in bar, what do I do? Let me look inside bar and see what do I do inside bar. In bar, I'm just touching the field f1 of the parameter p, storing some new object into that object's field f2. I don't touch this pointer, and I don't touch any other fields of the parameter p. So whatever is relevant from the value context for me is just this much. What is p pointing to and what is p dot f1 pointing to? I'm going to store something new over there. Similarly, at line 6, I had such a points to graph. Maybe it has multiple parameters, maybe it's much more deep and so on. But from that points to graph, only this portion is relevant for me. Now start looking. I have cut down the width of the graph by removing this pointer over here. I have cut down the depth of the graph as well by not caring about fields beyond F1. All right. So this is about relevance. It doesn't matter now if there were big points to graphs being passed to different or reachable at different cost to bar. I just need to compare this much part, what is pointed to by P and what is pointed to by P dot F1. The next idea we said is, should we specialize for the application? So we were trying to perform escape analysis. In escape analysis, the objective is to classify each object into two categories. Either the object escapes the scope in which it is allocated, or it does not escape. It's local, it's captured inside the scope, right? So let's say escapes is E, does not escape is D. Now, after identifying the relevant value context, even though this OA is different from OB, OI is not OK, OJ is not OL, what if none of them escape? And if my objective was to determine whether an object inside bar escapes by being stored into a parameters field, well, if the parameters do not escape, bar is inlined inside the collars, then I don't care if the points to graph is different, even if the relevant points to graph is different. I just need to care about the escape status of the objects which are reachable by P or P dot F1, so that I could just find out whether the new results that I would compute for bar, would they change if I reanalyze this method in a new context. Right? So this is what we said we would specialize the context that we have for a particular application, and after doing this we got some magic. I mean, those 512 gigabytes of RAM machines, we could just perform on 32 gigs of RAM. Let's say analysis that were not terminating in hours, we could terminate them in few minutes, and we got the result for context sensitive results for the whole application in few minutes for most of the Da Capo benchmarks, the real world programs that we had at the time, let's say. Okay. So this was interesting. We got magnitudes of improvement in time and memory by using two ideas. Find out what is relevant, maintain only that much of the data flow abstraction, and then specialize instead of performing general pointer analysis, probably try to specialize it for the application. So there are more such learnings in the paper, and there are few more which I would not describe in detail. First is, there are many analyses over the last 10 years which have tried to scale pointer analysis by staging it into multiple steps. Do get some information, use it to stage the next information, and 2 plus 2 becomes 1.5 sometimes instead of 4 or 5. Okay. So there are several other points which are discussed in the paper. All right. The last point I would look into is arguing correctness. So, well, we implement nice ideas, we present them formally, we describe their semantics, but then at the end of the day, is the proof of correctness enough when you want to take your implementation to a compiler? Right? Probably no. There are so many cases. Are we so confident of our engineering, of our implementation, of not introducing a bug in our implementation? Right? I mean, sometimes we should. At least I had to ask myself: am I convinced that my implementation is complete as well as sound? Nobody told me that there are more than 4 cases. Now I found 14. Could it be 15? Am I missing something? Right? Now, similarly, is the analysis sound? These were questions I had to ask in terms of my implementation, not only the theory. Right? So, can we resolve reflective calls precisely and soundly? In static analysis in Java, this is still an open question. We probably cannot. So, and then I was trying to apply static analysis, as I mentioned in the beginning of the talk, to JIT compilers. So if I do something statically and then use it in JIT, is it same as modular analysis? Okay, let me tell you why am I calling it modular analysis first. So JIT analysis basically are performed over the methods that are compiled at JIT time, and they are imprecise because you don't have the budget to analyze the whole program. On the other hand, if I want to perform static whole program analysis, I don't have libraries available. The code of the libraries can be different for different versions of the libraries. So I can perform intra-procedural analysis statically for the application and then scale it or complete it by including the analysis of the libraries while I move to the JIT. But is that analysis really a modular analysis itself, where I'm analyzing different modules one by one, maybe incrementally, and then combining the results later? So we learned that first thing, you can't perform static analysis of the whole program. So as I said, we did the same. We said whatever statically we could analyze, we would analyze, but we would not assume that libraries will never come to us. We would assume we would compute values conditional to the presence of libraries, and once the libraries are there, we would resolve the conditions in the VM and get the final answer. This way we could, in general, we can scale, we can get the analysis results of a scale of a precise analysis in a VM in a JIT setting without actually breaking down or without actually assuming conservative results for the libraries. We can solve the problem, but then, as I said, it looks very much like standard 20, 30 years old known modular compositional analysis, isn't it? Analyze few parts of the application and merge them together at the end. But probably it's not exactly the same. We were in fact this work was presented in UPSLA 19. It was part of 2 plus, and there is a correctness related issue which was pointed out there. Is it really sound to say that you can pause the analysis in a different setting in suit, let us say, and then finish the analysis in a VM? There were engineering challenges that we addressed already, but then is it okay to split the analysis in such stages? Is staging of an analysis across different environments correct, was a question. And then this is post onward 2020. We actually had a paper 2 days ago in SAS 2022 where we said that actually splitting this analysis the way we were doing it can be just seen as partial evaluation, and we said partial evaluation is known to be correct, so this is also correct. There are ways to handle some of the problems, so I'm not going into the details over there, but staging the analysis allows you to not only gain insights about a program like the one I talked about in the previous work, but staging the analysis also allows us to scale the analysis, because now you don't need to tackle the whole program at one time. You can divide it into libraries and the applications, and then there are arguments which can be used to say that it's not incorrect. It can be proved that staging in such a way is still correct. So this is one more thing which I wanted to highlight. To summarize some of the learnings, as I said, I cannot put all the small bullets from the paper on the slides. It would be useful. But just to summarize, one of the things is pointer analysis research is not going to die soon. It was interesting in 2001 when Michael Hind asked this question. It remains to be interesting even after 20 years. And advancements in pointer analysis, at least in my experience, won't land into production compilers unless we tame their unscalability further, especially in for JIT compilers. The other thing I would like to emphasize is probably we have spent a lot of time in trying to scale general points to analysis that is sound and precise for languages modern as Java. In fact, nowadays we like even more dynamic languages like R, JavaScript, Python, and so on. So probably we should instead of trying to scale general points to analysis, probably we should just compute what is needed specific to the application domain, like we did for escape analysis and some other analysis earlier. And probably this looks like a promising way to go ahead. This is conceptual, and in terms of implementation, getting insights about programs, breaking it down to stages, a single instead of doing everything together. As I said, 2 plus 2 might not be 4; it may become 1.5 if you break it down into multiple stages. So, or maybe 2.5. Okay. So these are few of the learnings that I have described in this onward paper. And as I said, this probably might be more useful, as the reviewers had pointed out at the time, to new scholars coming up in this area. But I'm sure as many papers are here are much more senior than me, or compared to new scholars, we can probably use some of these things as we guide our research in some of the things that we are doing. Right, so thank you.
I'll grab your microphone and then you can stand up here. Questions for us here? Any questions? Back there?
I have plenty of questions, so
Sure.
we gotta give someone else a chance after the first one. So can we go for a technical one on that? Can you show slide 13? So I'm trying to understand, because I didn't understand your technique here. You said you decided that a good insight is to find what's relevant in the value context.
Mm-hmm.
Like in this particular case, you only care about P of F1,
Mm-hmm.
right?
Mm-hmm.
But what's relevant in the value context is a client analysis over the pointer analysis. And it's not even monotonic, because you cannot just say, oh, I'm gonna expand it. It's not, if you find that the first level is relevant and you stop at that, then you lose all the precision, so you shouldn't even go any deeper. So my point is that think of the call to FB passing B as an argument, and suddenly the downstream function reads 7 more fields.
Exactly.
So how do you deal with that? I would expect that what you would say here is that you limit the value context to a specific depth statically.
Yeah. So this
But
was.
instead, you're saying something different.
No, so you have partly answered the question as well. So when we call FB over here, and if I pass something to FB, and at multiple levels down the line, if FB or any of its callees do something with a parameter, we do it interprocedurally, keep on adding the depth, and then we cut it down less based on whatever. So it's not just one level; it's all the callees down the line.
So you kind of say, if I'm not sure if it gets passed further, then I assume that the entire value context is relevant?
No.
Or-
So okay. So it's not based on it's not based on what would I do with it later. You pointed out about the application. Here it's about the relevance of the or the amount of depth of the caller's points to graph that I would be accessing in the callee, or transitively it's all callee. So we
But that's
interpret.
my point, that to
Yes.
get to the transitive
Yes.
in the colleague, you first need to do the pointer analysis so you know what virtual functions get called.
Yes.
etc. So that's what I don't understand how you approximate.
Right. So probably I didn't mention that fact. So the first one is based on the result of a imprecise pointer analysis, because if it was context sensitive in itself, then we are just trying to solve the same problem.
Okay,
that
so
yeah.
it is a staged analysis where you
Exactly.
look at an imprecise one. Fine.
Right.
Okay, so just to wrap up in your final conclusions, I think the one that's most conventional wisdom that most people will agree with, and I will try to disagree with, and that's my kind of mission, is your fourth bullet.
Mhm.
Obviously, static analysis, if you make it specific to the application domain, you can get tremendous results with much simpler analysis techniques, obviously. That's kind of something standard conventional wisdom. I think the challenge is to come up with good techniques that are agnostic to the application. And that's what I've been trying to do for years. As you know, like have a big knowledge system, however much memory it takes, all thousands of declarative rules, it infers up to a certain level what's true, and then you can specialize some specific clients. But certainly, if you have only one client, you can specialize quite a bit. But I think it's a very interesting challenge, and we have made a lot of progress in identifying the right kind of context sensitive, the right kind of precision abstractions that we can get useful, scalable precision, even without knowing whether you want to escape analysis or whether you want to taint analysis or whatever underneath.
In fact,
That's my point.
I won't disagree. In fact, I would say that sometimes more interesting. As a researcher, I find it more interesting to solve a problem which can be applied to different applications. That if I scale it to in such a way that it can be put up to use pointer analysis results in any application, I am happier as a researcher. In fact, instead of just targeting one application domain. So I don't disagree, and probably I also would keep on doing some such work in future. Either way.
Cool. Do we have any more questions?
So this is more of a comment than a question, but a really positive one. I did some pointer analysis in my thesis, and I discovered this fourth bullet that Jonas was disagreeing with in my own work. But I didn't write a paper about it. I think I mentioned it in a doctoral symposium talk in the early noughts. But I think getting these lessons, some of these are very enduring. Some of these might be completely unique to you, which is great. But getting them on paper and helping other people learn from them is a wonderful thing for the community. So thank you for doing that.
Thanks
I
for the comment.
now want to read your paper and pass it on the other lessons to my students.
Thanks a lot. I'm happy to have contributed something useful.